Well, thank you so much for having me for this exciting Flash Talk segment. Today, I'll be sharing some of our new exploratory work, which is exploring interfacial mineralization using new fib preparation techniques for liquid-TEM. And this work was conducted and has been ongoing since the end of my PhD at McMaster to where I am now at University of Waterloo. So I'm finally, very excited to share a little bit of it through this series. And so, as I mentioned, this research began when I was with the team of Catherine Grenfield at McMaster University, which is situated in Southern Ontario, and where the team's overarching focus is this multi-scale microscopy of biomaterials theme, which includes research areas in biomaterials, biointerfaces, and biomineralization. And McMaster is always very lucky to have and be the home of the Canadian Centre for Electron Microscopy, where all the imaging was done for this that's featured in this presentation today. And so, as I mentioned, we wrapped this project up where I am in my new role, and I'm thrilled to share that I've joined the University of Waterloo as an assistant professor just this past January and launched my team, which is known as the Regenerative Biomaterials Innovation Group. And we're already getting started on some pretty exciting research, which themes around liquid phase characterization, biomimetic inspiration for tunable implants, and still true to my heart, continuing with exploring biomineralization mechanisms. And this is my last little plug. I'm just sharing that as a new PI, I will be recruiting. University of Waterloo is one of Canada's largest engineering programs. We're home to some very great resources in microscopy, additive manufacturing, and nanofabrication, as well as lots of other exciting things. And we're not too far from the CCEM at McMaster as well. We're less than an hour away. Anyways, back to business. So in today's talk, I'm just going to start off. I think our research is a little different than a lot of people that have been in these flash talks so far. So I'll give a little bit of a motivation and background to this and why studying calcium phosphate mineralization processes are so important. Then we'll get into the nitty gritty. We're here in a flash talk to talk about some of the liquid-TEM work we're doing. And so we're going to dive into how we were able to observe interfacial mineralization reactions dynamically. And then we'll give some snippets of some of our recent research where we're kind of starting to explore and dive using liquid-TEM to study what affects and influences interfacial biomineralization of biomaterials. And so a lot of our work centers around bone, and it's a quite significant thing to study. I mean, we all have bones in our body, but we can kind of motivate this research in a lot of ways. If we're talking about mineralization diseases and related to hard tissues, we have osteoporosis, which is estimated to affect over 20% of the population over 50 and is predominantly in women too. So, personal motivation there. Total hip and knee joint replacements are up. These are anticipated to increase quite a bit over in the next 20 years about. In the US alone, there's over 1.5 million new spinal fractures annually, over 1 million dental implants placed in North America, where we usually see about a 95% success rate, but that 5% is quite significant, and it helps highlight our need to develop better biomaterials. And of course, there's a number of diseases that are affected in bone, cancer, rare bone diseases, diabetes, and more, which all impact this. And when I'm talking about bone, I'm not going to dive too much into this, but it's got this beautiful multi-scale structure that's hierarchical from the macro scale all the way to the atomic scale. It's kind of like a tree with branches and lamellar sheet structures. But as a material scientist, you can kind of think of this as a simple biocomposite, but it's not simple by any means. But at the nanoscale, we're really talking about what I'm more interested in my research is the collagen collagen, which is kind of your polymer phase, and these hydroxyapatite crystals, which is like a ceramic phase. And hydroxyapatite is our calcium phosphate mineral that its distribution and extent are essential for the mechanical properties of hard tissues. But we don't know where everything is or how it gets there. And so that's a big theme to trying to explore these processes. And understanding these mechanisms can help shed light, improving osseointegration of implants, diseases, and provide new pathways for treatment. Now, Liquid-TEM in the last, I gotta say, like maybe 7 years has been essential for exploring these processes with calcium phosphate. It's a powerful tool, as many of you know, to study biological samples in native hydrated environments and in situ reactions taking place dynamically. Our team had some research at first in 2018 that was published where there were the first Xiaoyu Wang was one of the first people to kind of highlight from the team these calcium phosphate mineralization events dynamically. I continued a lot of this work, building onto this foundation, adding different mimics such as polyaspartic acid and collagen to understand hard tissue mineralization further. Of course, I can't not mention at least one thing from Jim DiIorio's team. Jin and all in 2021 had this wonderful work showing the dissolution of amorphous calcium phosphate precursors that followed the precipitation of hydroxyapatite. There was wonderful work by DiCecco and all showing different multiphasic pathways for calcium phosphate. In any case, there's a lot of work out there right now that's kind of emerging, which is really great. You can check out our review paper that covers this and other biomineralization systems that have been studied in Liquid-TEM. But I'd highlight that these pathways still not fully understood, and limited in situ research has considered the influences of interfaces in these mineralization processes, which are critical for nucleation and studying crystallization events in real life scenarios. And so this research project really started with us asking how we can dynamically observe mineralization at biomaterials interfaces, and we recently published a perspective on the topic in Nano Letters, and we've just expanded this work by submitting a full-on methodology piece with Microscopy Today, which is set to come out, I believe, in March, so pay attention for that, which will have a lot of these details if you're interested in this work. For our Liquid-TEM, we are using our protochips Poseidon Select Holder for this, and we are using these with the heating chips, and so this allows us to heat at 37 degrees in these experiments to mimic physiological relevant conditions, and we are pairing that with a bottom E-chip that we'll talk about in a little bit, but this has a 150 nanometer spacer for it. So we decided to use FIB methods, focused ion beam methods, to prepare our thin foil biomaterial for this case study. And the FIB, I will say, it was led by our amazing colleague Travis Casagandre from the CCM, who really came through with creative ideas to develop easier workflows for our system. This is kind of more of his brainchild, and he would be able to better explain this more. So I'm just going to breeze by a lot of this, but you can read our Microscopy Today paper and our perspective to get more insights into this work. And I will say we didn't start from zero as well. There is a guide provided by Protochips that helped us in our initial planning, but we did differ from this guide, which I'll go through in a little bit. So in a quick summary, we did use conventional fib milling techniques to produce our titanium lamella, and this used a relatively short tungsten layer in the study. Unconventionally, we did extract the lamella on the far side of the chip. This allowed us easier attachment onto our E-chips or bottom E-chip later on, and so that facilitated the attachment. Now, in this work, we are using the Protochips pre-tilted stub, and so that helped with the workflows and, very delicately handling the E-chips as well. And so we removed the E-chip and attached it to the side of the, or we removed the lamella and attached it to the side of the E-chip for our polishing directly. And then we did detach it. And so this is kind of showing this process. And so we did detach it once it was near the final sort of polishing stages. And while it was attached on the micromanipulator, we rounded the corners to avoid any sharp edges that could pierce the membrane of our E-chip and cause damage to it. And we at this point did a final polish in air, like in vacuum, I guess, on the micromanipulator and ensured that the capping layer was removed. And then before mentioning this final attachment step, I did want to bring up something that's different in this study is unlike a lot of the works that have done FIB workflows for electrochemistry purposes, our focus is really on the lamella itself. And so we focused on using the small E-chips in this configuration, which honestly are way less expensive than the electrochemistry E-chips or the heating E-chips, for example. And so that way, anyone who does FIBS knows accidents happen, and we wanted to avoid expensive accidents in case we damaged any of the electrical leads or the membrane itself. And so we chose to do the attachment on the smaller E-chip, which differs from the guide provided. But because we had that 150 spacer, we did have a limitation during the attachment where we didn't want anything to be over 150 nanometers. We didn't want to cause any uneven pressures in situ. We wanted it to be kind of a very thin liquid layer. So in the attachment itself, we avoided adding paddings to attach the E-chip and instead did a redeposition fusing method using ion beam stitching. And this also let us attach the lamella closer to the edge of the membrane window, which is not recommended by the guide, but we were able to do it. And it also helped us avoid contamination onto the membrane and titanium itself, which would come from beam-induced gas deposition from the GRF. So in any case, so here's our Liquid-TEM configuration. This is pretty standard. We did remove the photoresist before FIB, but we freshly plasma cleaned the E-chips right before Liquid-TEM assembly. We're using the two E-chips in parallel configuration to maximize our viewing area. We added about 0.5 microliters of our mineralization solution before assembly and incubated for about a minute before removing excess solution prior to putting the enclosure together. We are using a mineralization solution that we have experience studying quite a bit. This is described in our papers. But yeah, in any case, this is the configuration, what the cross section looks like, and pretty much we've got that lift out, poking out on the side, and that's really where our focus area is. Not getting into too much of the nitty-gritty with our details here, but I'd just like to highlight that we are keeping our electron dosage relatively low. Calcium phosphate is on the lighter side of minerals. And we didn't use Axon for this particular study, but the facility itself is using the Axon dose holder to regularly calibrate a lot of our TEMs. And so that's how we're kind of ensuring that these dose measurements are accurate. So what did we see? Let's dive into a little bit of the results before closing down. So at the start, this is kind of what we looked like, and anyone who does FIB work knows anything could go wrong, and we're really happy to see the FIB lamella, the titanium still remained attached and didn't detach at any point during these processes. At later points, so we heated it at 37, observed mineralization events, and we could see that minerals started to form in the local surrounding area, and more so seemingly on the titanium lift out. So that was really exciting. We were able to capture dynamic mineralization events throughout the whole session. This is just a snapshot video that's about covering like about a minute or two of imaging, but it's just highlighting that we have active movement and there's even biomineralization events happening on the surface of the titanium. We did also note, I mean, we couldn't create a perfectly smooth lift out, but we saw that nano rough areas seem to promote the adhesion of these nanoparticles more, which is kind of really exciting, still in exploratory phases, but has some relevance to implant research where people are exploring nanotexture for implant and biomaterial development. Key thing to note, and this is described more in the paper in detail, but confinement and beam exposure still must be considered when we're considering this kind of system as a whole. And so this is exploratory work, but I think that this could be some really exciting work in future to continue on. For post-situ analysis, this is facilitated using the protochips inspection holder. And so we did some post-situ. Here's 2 of the lamellas reproduced. And we highlight that we could do some really nice EDS showing that the calcium phosphate minerals are present, and do some diffraction analysis as well. And this just highlights what's kind of interesting is we are seeing some amorphous and crystalline calcium phosphate mineral attaching to these surfaces, and this relates more relevantly to biomineralization mechanisms, and where we're highlighting that there are some multiphasic pathways here. So in summary, I hope that you enjoyed the talk. This little flash talk, we covered a bit of a motivation that's a little different, and why we're interested in studying calcium phosphate mineralization processes. I talked about the methodology behind it and how we were able to observe these interfacial reactions. Then we covered some very quick snapshots of the results. I highlight, please go to our paper and see more. And the thing I do want to emphasize is, while this is still exploratory, this methodology is broadly applicable for studying thin foil materials and their interactions in situ in liquid conditions. So thank you so much for your attention, especially Protochips for inviting me to give this talk, our funding agencies. This project wouldn't be possible if it wasn't for ACS and their Nano Letters Seed Grant, which I was the inaugural recipient for the North America competition. Also big help from the CCM. Of course, Travis helped amazingly and is a co-author on all this work. But we did get assistance in some of the TEM when I left, with Jang and Carmen working together. And thank you to the Grenfell Research Group, and of course, Ellie Sohn, who's given me some feedback and insights in the early project planning. So thank you so much for your attention. Feel free to connect and reach out if you have any other questions. So have a good day.